Hello students, welcome back to the SAITM online learning platform. I, Kirti Sharma, am working as an assistant professor in St. Andrews Institute of Technology and Management, Gurugram. Today in the lecture series of Design and Analysis of Algorithms, we will discuss the last unit of your syllabus. There are some topics to discuss. It's very small unit actually, so each and every topic that we will discuss is very important. Actually, one main topic is there. Every remaining topics are as a subtopics itself, right? So you just have patience and just stay tuned with the next lecture also in order to get the clarity. Actually, this particular topic, complexity classes, which consists of some classes like P problem, NP, NP hard, NP complete, some NP completeness. Here this NP completeness is important because Cook's theorem is a important topic here. Like it's also known as the Cook's theorem here. So Cook's theorem is important one here. So NP completeness is also known as given by the Cook scientist here. So we will discuss these things with the help of examples. So it's very like a confusing topic, but if you will listen this complete whole lectures starting from this and next one, in within the two lectures I will ensure you the clarity about each and every small things here. So it will help you in your university exam as well as in the competitive exam point of view also. So stay tuned with the lecture. So let's start with the complexity. Before starting the complexity classes, I want to create some basic, you know already, like some polynomial problems. Polynomial problems are there. So there are some problems like polynomial time problem and exponential time problems. Like if we are solving these searching problem, linear search, binary search in some time like n log n, n square, n cube, n log n. Linear, we know very well. Like binary search gives the best to at the log n time it take to execute the algorithm or in searching any key element, right? And in the sorting, merge sort give the best performance like n log n it will take to sort the number of list of the numbers, right? So like if I'm writing n square, n cube, or n log n, or n raised to power 10, it could be n raised to power 100, or anything. All will come under the polynomial time problems, right? And in exponential, like 0, 1 knapsack problem, 2 raised to power n is the time complexity here. Any constant could be said like m into n into 2 raised to power n, or anything else can be there. But I'm just telling you about the exponential time. So 2 raised to power n something, if I'm taking it, that is exponential time. So all these algorithms are exponential time taking algorithms, and these are the polynomial time algorithms. So why I'm telling it to you? So our main purpose, that is actually research level topic, in which further research can be possible, like various searching sorting algorithms are there which are taking some time, like if you can solve any problem in polynomial time. And deterministic algorithm is there. Two words are there that we will discuss in the definition further in the P class and N class: deterministic and non-deterministic. Deterministic means here you know, like there is no any kind of dilemma in writing the algorithm of any problem, then it's called deterministic problem. And what about the non-deterministic? If you have any dilemma, you have some confusion, you are writing the problem algorithm for the problem, but you don't know the exact solution or exact solution for the problem, but even though you are writing the possibility to solve that problem, right? So in the form of algorithm. So it's the difference here. So if any problem is there belongs to the polynomial time, that means you can solve that problem in that is a deterministic having the deterministic algorithm that you can solve in the polynomial time. And here in exponential case, there are the problems which having the non-deterministic algorithm that can be solved in the polynomial time. So not to confuse like polynomial, both the types of the problems we need to solve in the polynomial time only, right? So our main purpose is either solve all the exponential time algorithms, find the non-deterministic algorithm for them which can be solved in the polynomial time. If it is possible, then it's good to, like in the for the research point of view, if you are able to find the solution of that kind of problem, it's good. You are able to find the non-deterministic algorithm itself in the with the as a solution of the problem of the exponential time problem, and now they are solving into the polynomial time. So you are converting it in this form. If you are not able to find the solution exactly in this form, now you have to relate it as like some problem. Like if you are able to solve any of the one of the problem among all these problems, exponential time problem, within in the polynomial time, then you can relate that problem with the leftover all the problems in order to make give the surety. Like if one problem that belongs to that category is solvable, then leftover problems can also be solvable. So in that case, you have to establish the relationship with the all remaining problems in this category. So there are two main objectives here: either find the write the non-deterministic algorithm in order to solve it into the polynomial time for these exponential time algorithms, or next thing, if you are not able to write the algorithm, then find the relationship of exponential time problem to the polynomial time problems. So either find the relationship. First we will check it out, like is there any possibility to write the non-deterministic algorithm or not in polynomial time that can be solved in polynomial time. Then after, if it is not possible, we will find the relationship, right? So now what about the non-deterministic algorithm? How we can write the non-deterministic algorithm? I'm taking here an example for the non-deterministic algorithm. Non-deterministic means there is a right. So there is a algorithm, but solution doesn't exist. Algorithm exists for a problem, but solution doesn't exist, right? So there is a kind of dilemma here, confusion here, right? So in order to solve the to find the solution of the problem, so I'm taking here a searching problem that I'm naming it as a nsearch. Just it's an example, like if you want to search an element, rather taking any predefined algorithm, I'm just creating a new one in order to reduce the time, like in order to solve it into the polynomial time, right? So if this is a problem here, sorry, algorithm here for any problem, then what we have to do here, like try to understand this algorithm here. This is an algorithm for the searching any key element. A is the array, n is the number of elements, key is the searching element for which we are searching in the list of array. Right? Here, choice is a function, and then success is a function, and then failure. Let's assume all are taking the 1 constant time. So order of 1 will be the time complexity. And we know the binary search algorithm in the searching case giving the best possibility, that is taking the n log n time, right? And what we need, if any searching is taking the constant time, that means it is the best search. That is the that should be the main objective. Whoever is doing the research in this field, in order to find the best searching algorithm, that is like as comparative to the that whatever is existing there right now, right? So let's assume I have taken this non-deterministic. That means it may possible to find or to be there like any algorithm which having the constant time complexity. But what can be possible, that we don't know actually. That is the problem. That's why it comes under the non-deterministic category. That means right now we don't know about it. We have the question mark at this, filling the blanks at that place, but in future it may possible there will be some answer for that, right? What it mean actually, here this choice is a blank space here. Like that means there is a function that is providing the index to the j value. So that j value is exactly giving you the key element, right? A of j index value providing you the key element. If it is that key element for which you are searching, then your search is successfully. Otherwise, failure is there, right? So what it means, this choice, how it is finding the exact key element, that is the main question mark here. So right now we don't know about this particular functionality, how it is giving us the exact key value for comparison, right? So it is taking constant time, but what is the exact solution for this choice functionality? We don't know. That's why it is a non-deterministic algorithm, but it can be solved in the polynomial time, and it is taking the lesser time comparatively to the existing one searching algorithm, that is order of one constant time, right? That we actually want in order to do the research work in this field. We want this thing only, right? So we will discuss now some P class and P class problems. Then we will take the some base problem in order to find to relate to establish the relation. So up to now, first point is clear, like either write the non-deterministic algorithm as we have written any searching algorithm, rather than like if there is a question mark, it's okay. If it it's possible, but we are writing it now, so it's okay. We are writing it in the polynomial time. There is any solution that is possible. Right now we don't have any answer for this particular functionality, how it is finding the answer. Like if I'm taking an array A here, which consists of some element 10, 5, 6, 9. A is an array. There are 4 elements here, and what it is, this key, for example, G value is provided in the J. This choice value is providing this particular element. That means that index value. If I'm assuming it 1, 2, 3, 4 index, so it's giving J to the 2. What it means? J is 2. That means A of 2 is value 5. Key value is 5. Is it the same value for which we are searching? Yes, then it will give you answer. So how you can find it out, like how this particular index value choice function is providing you? That is the main question mark here. That's why it's non-deterministic. I have already also taken an example here to give the clarity about it. So first point is clear. Either write the non-deterministic algorithm for the problem, whatever you are having. Like our problem is to find the searching algorithm that provide the best time complexity or less time that take the less time comparative to the existing one searching algorithm. Like we are taking binary search algorithm for an example, like, right? But right now we don't have any answer for this choice functionality, but we can put it as a showpiece here. Like up to now we have done this much work. In future upcoming researchers, newcomers may search it out, no need to find out the algorithm, but they can directly take the concept from here and do the work, they can do the work to find out the functionality of this choice here itself, right? So that will help you help the researchers that are that may find the functionality of the choice in future, right? So solution is possible, but right now we don't have any solution. That's why that algorithm can be solved in polynomial time, but this is non-deterministic algorithm, right? So next we are moving. If it is not possible to find the non-deterministic algorithm, then what to do next? So for that purpose, what we have, for that purpose, we have to establish the relationship between exponential time taking problems to the polynomial time taking problems. How we can establish the relationship, that we will discuss later. Before that, we will discuss like about the different classes or categories. Then after we will relate we will take some base problem, satisfiability problem, and try to establish the relationship of the exponential. Like either they we have already solved like 0, 1 app set. Then we have already taken the example traveling salesman, SOS sum of subset, graph coloring problem, right? So we will take, like if we will take some base problem, and we will I will relate that base problem with the 0, 1 app set problem. If it is possible to relate 0, 1 app set that with a particular satisfiability problem that already defined, so if we are able to establish a relationship in between them, then other algorithm can also be solved in the polynomial time, right? If we are finding the solution, polynomial time solution for the one, then for the others also it is possible, right? So like definitions of the NP class problem. So set of all the possible decision based problems, we are dividing here into some solve that who cannot solve, which cannot solve or produce any output within the polynomial time. But main thing here, verifiable but verified in the polynomial time. What it mean? NP class problem. What is NP class problem? NP class problem are those problem which cannot solve or which cannot find the output of any problem within the polynomial time, but can verify, as we have already taken a non-deterministic searching algorithm where we cannot find the exact solution, but we can verify that it will do the work perfectly if it will execute. If we know the how choice function is working, then we can get the order of one time complexity, and we can solve it in the lesser time. So it's clear to us, but how is not clear for us, right? And P is the subset of it. P class as a subset here. NP problems being hard to solve. So NP doesn't mean here not polynomial. Mark this thing. It doesn't mean N stands for not and this is polynomial. No. Originally it means non-deterministic polynomial. That means N stands for non-deterministic and P is a polynomial. So it means according to one input number of the output will be produced. That means non-deterministic, right, polynomial algorithm, right? So these are the problems which are hard to solve, but non-deterministic, having the non-deterministic algorithms about the NP. Now what about the P class problems? There are some divisions now. So first division we have already like discussed, NP class problem. Now what about the P class problems? This is also set of decision based problem that comes into the division of the P problem. Who can solve in the polynomial time? That type of problem are easy to solve and comes in this category. The problems which are easy to solve and can find the solution in polynomial time comes under the category of P class problem, right? So what about definition of the polynomial time? If we produce an output according to the given input within specific amount of time, like timing is fixed, within that much time we will get the output of this problem, right? That kind of problem or that is known as a polynomial time. If we know it is possible to find the solution, but in how much amount of time we don't know, right? That type of problem is known as exponential time problem, you can say, or non-polynomial. So that non-deterministic polynomial time problems, right? So non-deterministic polynomial time problem don't have the specific amount of time in order to solve a problem, right? So next thing that we have here, non-polynomial time, as we have already discussed about it also. Non-polynomial time, like if we can produce an output according to the given input and there is no time constraint here, that type of problem is non-polynomial time. But mark one thing, the output can be in the form of yes, we will produce, but time is not fixed. We are ensuring it through the non-deterministic algorithm. It can be solved, but time is not fixed. That type of problem comes in the category of the NP class problem, right? So we will discuss these things in this detail with the help of example also. So now what is the meaning of the decision based problem? Actually, in the decision based problem, if its output is a simple, you can say yes or no, or you need to say this like true or false, 0, 1, or in the form of acceptance and rejection. Like, is it possible to find the solution of this problem? Yes or no. If you are able to give that answer, that means that type of problem is known as decision based problem. So we will phrase many optimization problem as a decision problem. Like I've already give you an example, some 3D and dynamic programming, graph solving problem, Hamiltonian cycle problem that we will discuss in this, like as a decision based problem for which we can give the answers is in yes or no. Is there any solution exists for the problem or not? This type of problems are known as decision based problem that we will discuss here in order to give the categorization or class in the different classes that we have right now as a complexity classes, right? So what about the NP hard and NP complete? Most interesting to know about these two problems, NP hard and NP complete classes, right? So the problems here which satisfy the points to come into the division of NP hard is, first point, if we can solve the problem in polynomial time, then we can solve all the NP problems in polynomial time. I've already told you this thing, right? If you convert the issue of one problem into the another within polynomial time problem, so if we have an problem which is NP class NP problem, like we cannot find the solution in the polynomial time, but we can convert that problem into the problem which can be solved in the polynomial time. Then also it comes under the category of NP hard class. So these 2 points must satisfy. What about the NP complete class? First thing, it should be, the problem should be in the NP, must be in the NP category and NP hard category. So if any problem is existing in both of them, it is in the NP class and NP hard, then that type of that problem we can say it's a NP class, NP complete class problem, right? That problem will exist in the NPC class. So we will take a diagram here in order to give you the clarity. Here I'm taking here in a diagram. So this diagram is representing here, like this is NP hard problem, hardest problem to solve. The type of problem like quantified Boolean formula function, like satisfiability problem that I'm taking here, CNF conjunction normal form, quantifiable Boolean formula like formation is there. That type of problem comes under the NP hard problem. So no Hamiltonian cycle. To find out like there should not be any Hamiltonian cycle, the type of problem. And NPC problem, I've already told you, if any problem is NP and NP hard, then you can say it's NP complete problem here, intersection of both of them, NP hard and NP problem. So NP complete problem having the satisfiability problem, 0-1 knapsack problem, Hamiltonian cycle problem. If you have to find the a graph like which is not having the Hamiltonian cycle, it's hard to find. But to find the Hamiltonian cycle problem, that we have already discussed in the last lectures, like how to find in dynamic programming section, how to find the solution to, in order to find out the Hamiltonian cycle. These type of problems comes under the category of NPC, NP complete problem. NP problem, graph isomorphism, if you have to find P class problem here. P is a subset of the NP here. So MST, minimum spanning tree, storage connectivity, this type of problems comes into the category of P class. So easy problems that can be solved in polynomial time come here in the P, it will come here in the P class. One more interesting diagram is there. You can see this diagram in like books also. Most wanted diagram it is actually. This is P, this is NP, and I'm writing here this is NP hard, and this intersection part is this is NP complete, right? So this is also next way or alternate way to represent these classes. So what it's mean actually, this P is a subset of NP and the common whatever, if a problem is NP and NP hard, then you can say it's a NP complete problem, right? This P is not fixed here, it always increases its size as we are getting the problems which can be solved in the polynomial time. This particular P class will extend its boundary, right? It will expand its boundary, and it may possible like this P will become equals to the NP in future, because all the non-deterministic polynomial time algorithm, it may possible it will become the polynomial time, because I have already mentioned to you right now they are not in unsolvable form. Whatever is there in the NP problem right now, we don't have the solution, but we know there exists a solution, but in how much amount of time we can find it, we don't know actually. So that's why this P reason will extend in future as the research work in this field will expand, right? So if any problem is undefined right now, it will define in future itself, right? So this P will increase its boundary, right? So at some time this P, right now this P is a subset of the NP, but at after some time it may possible this, it will possible like this N is equals to NP will become NP. That means N class will become equals to NP. The famous scientist, you can say Cook's. So in the Cook's theorem, it is mentioned that he has proved even this thing, this N is equals to NP with each and every by taking an example itself, right? So the cases are defined here in the Cook's theorem. The completeness problem it is actually, so that will show that how the relationship exists in between the N and NP, how they are equal. So the possibility in future to be equal both the classes are shown by the Cook's here in his theorem, right? So that we will discuss later. So for the right now, I hope the basics is clear to all of you. Now move to the next thing here, polynomial time verification. So what it's mean actually, I have already told you, solve in polynomial time, NP complete problems. If before talking about the NP complete problem, it is essential to introduce the notion of verification of the algorithms. So many problems are hard to solve, we know, but they have property that it easy to authenticate the solution if one is provided. Like if any problem is there, hard to solve, but solution is existing. So we are ensuring it, we are giving the verification. If this kind of algorithm that we have already seen the searching algorithm previously, we have written the non-deterministic searching algorithm from which we were saying like this, there is a solution exists if you solve the choice functionality here. So we are verifying the solution, like it is possible to solve this, to find the searching, to write the searching algorithm that is taking order of one constant time, but we are authenticating it, verifying it, but right now solution doesn't exist and it is hard to solve. So that type of things is known as polynomial time verification. Verification, you are giving the unsurety to solve the problem. That is a verification. You are verifying but not providing the solution. But you are giving the verification that if the solution is exist, it will be right one, right? So it will like save the time of upcoming researcher in order to finding out is it right to solve it or is it is not right to solve it. So it's a kind of verification problem, right? So Hamiltonian cycle problem, as we consider the Hamiltonian cycle problem, there are undirected graph doesn't have a cycle that visit each vertex exactly once. There is no known polynomial time algorithm for this dispute, right? So note here one thing, it means you cannot build a Hamiltonian cycle in a graph with polynomial time taking. Even if there is no specific path is given for Hamiltonian cycle with particular vertex, yet you cannot verify the Hamiltonian cycle within the polynomial time. Right? This is an example in order to give you the clarity about the polynomial time verification, right? So next, like we have the Hamiltonian, non-Hamiltonian cycle, Hamiltonian cycle. So here in this graph, we can understand like this. We can take this graph as a Hamiltonian cycle, and it would be easy for someone to convince this. They would similar say the periods is having this at 3, vertex 3, vertex 7, vertex 1, 1, 3. So this particular path that is highlighted here, this one path, right? So we could then inspect the graph and check this is check that this is a indeed a legal cycle and that it visits all the vertices of the graph exactly once. If even though we know no sufficient way to solve the Hamiltonian cycle problem, there is a beneficial way to verify the given cycle is Hamiltonian cycle, right? So write a note here, like for verification in the polynomial time of an undirectional Hamiltonian cycle graph, there must be exact specific definite path must be there given that giving a Hamiltonian cycle. Then you can verify that it is solvable in the polynomial time, right? So it's a kind of verification for polynomial time solving algorithm. So next is what we have a relation between P and NP class problem. So NP and NP class problem, that is itself a Cook's theorem try to prove it. So observe that P contains in NP, as we know this is NP and this is P, this is P and this is NP, right? We can indeed like verify the solution in polynomial time. Like, we do not need to see a certificate here. There is no need to specify the vertex, intermediate set, like specific path to solve the problem. We can explain it in polynomial time anyway. However, it is not known up to now that it is equals to NP, like P is equals to NP. But it seems you can verify and produce an output of the set of decision problems that are in NP class that can be solved in near future in the polynomial time. So which is impossible because according to definition of NP class, you can verify the solution within polynomial time. So this relation can never be held up to now, right? So in future, it may possible they becomes equals. So Cook's theorem given the reduction functionality here in order to give you the clarity about this thing. So if reduction problem exists, like in order to establish the relation between the exponential time algorithms, like if we will take the one base problem and we will able to, we will relate the exponential problem, one of the exponential problem with the base problem, if we will successfully able to find out the solution for that exponential problem in the polynomial time by relating it by relating it with the base problem, then we can also relate, like if one problem can have a solution in polynomial time among all exponential, then left over other can also be reduced in that form. So that's why the concept of reduction comes into the existence here, right? So the class NP complete problem consists of a set of decision problem, like a subset of a class NP that we know. This is P, this is NP, and this is NPC. This particular part is NPC. So of course NPC is also subset of NP, right? So no one knows like how to solve it efficiently, but if there were a polynomial solution for a single NP complete problem, then every problem that belongs to NP is having the that can be solved in the polynomial time. So that's why for this we need the concept of reduction. Suppose there are two problems A and B, and you know it is impossible to solve the problem A in polynomial time, but you want to prove that B cannot be explained in polynomial time. So we want to show that A doesn't belong to the P class, therefore B also not belongs to the P class. If we are taking A and B two problems, right? So if A is not in the P class, then B will not also be in the P class, right? So we have to solve it. So that's why reduction comes into existence, and the following problem is well known to be the NP complete problem. So can take an example as a coloring problem. Three colors we have to color the vertices, and three color problem. This is not a three color problem. So we can establish we can reduce the different problems, like we can take two problems and we can reduce it. Let's take an example together. For example, I'm taking here a base problem that is already defined. I'm taking here a base problem that is already defined. That is our satisfiability problem. Satisfiability problem. Right? This is already predefined problem, right? So what it is actually, here in satisfiability problem we are taking CNF, that is conjunction normal form. Here conjunction means, you know, I think, and or that we will use. For example, I'm taking here a conjunction normal form CNF, and two clauses we are taking here. What are those two clauses? I'm taking here x1 disjunction x2 bar disjunction x3, then conjunction x1 bar disjunction x2, this, or you can say disjunction, right? And you can say conjunction. These are the two clauses C1 and C2 here, right? This is a CNF problem. We have to find it out, like this problem is giving, then it is giving the true as a answer for this particular statement CNF, right? So we have three variables here, so that's why it's known as 3CNF problem, right? There is three variables here, that's why 3CNF. If there are two variables, then 2CNF. If there are four variables, then we'll take 4CNF, right? So here for the example, we can take any CNF. I'm taking here 3CNF problem here, right? So if we want to take here, like how many total possibilities are there in order to find like this particular statement is giving the true answer. So x1, x2, x3, three variables are there. So how many possibilities are there? 0, 0, 1, 0, 1, 0, 0, 1, 1. We know all the possibility. For three variables, how many solutions we can have? 8 solution we can have. That means 2 raised to power 3 solution. So from which we can find it out, like any one of the solution is giving the right answer here, like for which particular condition this particular condition is giving the true answer, right? That we have to find it out. So how many solutions exist here? That means 2 raised to power 3. If we have the n CNF, so how many time it will take? It take 2 raised to power n, that is exponential time problem. That means satisfiability problem exists in which category? Exponential time category. And remaining 0, 1, knapsack, TSP, SOS, subset, sum of subset, traveling salesman, graph coloring, Hamiltonian cycle, all belong to the exponential time, and we want to solve them. So if we will solve the satisfiability problem, that is also an exponential time taking problem that we know now. So if this particular problem is solvable, then other one also we can solvable. We can establish a relation in between them. We can relate them if it is solvable, right? So let's try to draw the state space tree diagram for this particular problem. So I'm just trying to put here, like I'm taking here node that is describing, I'm trying to put the state space tree diagram here. If I'm taking it as 0, 1, 0, the next 1, 0, The next 1 0 1 0 1 0 1 0. How many times we have to take this 1 0? Of course, there should be the 8 solutions. We have already seen 2 raised to power 3. So this is a one path. I'm just changing the color. This is a one path. 1 2 3 4, and this one is 4. This one is 5. This one is 6, and this one is 7. And I think something is left here. 1 2 3 4 5 6 7 8. Total is 8. 8 solutions we have drawn here in the state space diagram. So state space tree, we know it provides you all the possible solution, among which one we will select as a path which is giving you the exact answer of the problem, right? The optimization problem, we have already studied this type of things, right? So if this is a state space tree diagram for the satisfiability problem CNF to provide the right solution, so now it's time to relate it. It is solvable if we are able to find it out the state space tree diagram. Then we can solve this satisfiability problem in the polynomial time. Now it's time to relate this particular exponential problem with the existing other exponential problem. So now I'm taking here an example as a 0 for the 0 1 knapsack problem in order to relate it, right? So what about the 0 1 knapsack problem actually? What it is here in the 0 1 knapsack problem? Like there is a profit, some profits available here. Like I'm taking an example, we have already discussed it. You can do the cross check. Profit is here, weight is here, 5 4 3, right? And here our main purpose is like either we have to include 0 1 problem, either we have to include it or exclude it. Either we have to include the next object or exclude it. There are 3 objects, either we can exclude it or include it, right? So how many solutions exist here? So if three variables are there, so 1 2 3 4 5 6, so you can relate it here. How many solutions are existing here? So for each and every there are 2 problems, like you can take it or you can leave it, you can take it or you can leave it. If we are taking here like solution here for the states, we have to draw the state space free for the 0 1 knapsack problem. We have already seen the state space free diagram for the 0 1 knapsack problem in the previous lecture. You can go back and you can trace it, and or you can make it yourself also, right? So if I'm not removing all the things from here, not CNF, not 0 1, if we are directly seeing this state space free diagram, this space free diagram is indicating the both problems for the both the problems for satisfiability as well as 0 1 knapsack. So this particular state free diagram is showing representing the both of them problems. So that means we can reduce the one problem into the another problem. So I think up to now our main task is completed. So we can reduce this particular part, one problem into the another problem. Now it's time to time of reduction. So how we can reduce it? Like for example, I'm taking here satisfiability problem, SAT, right? Satisfiability problem, and I'm assuming it's hard to find the solution. So for NP hard, I'm just using a word here. Let me use a word. It's a hard to find it out. So that's why I'm taking it NP hard problem. If I'm taking the symbol is for the reduction, 0 1, it can be reduced in the 0 1 knapsack problem, right? What it means, you can convert this particular problem into with polynomial time problem, right? In the polynomial time, during conversion is polynomial time problem. If this is NP hard problem, then it will also be NP hard problem. That is the meaning of reduction. If one problem that we are taking as a base problem, this is NP hard problem, then 101% you can directly say the problem that in which we are trying to reduce it, it will also be NP hard problem, right? So let's assume I'm taking here indicating I1 is a problem, reduction, I2 is a problem, and I'm saying here this is can be solvable in polynomial time. During the conversion, I'm saying this is NP hard. Then this one is also NP hard. You can directly say. If I'm saying here satisfiability can be reduced to L problem, and then this L problem will also be. I'm not taking here 0 1. You can take anything. If I'm taking any unknown problem also, L problem also, then also we will say this will also be NP hard. And one more thing, this particular reduction, it follows the transitivity connection here. Like satisfiability can be reduced in L1 problem and L1 is reducible to the L2. Then we will say this L2 is also NP-hard problem because of it follows transitivity, right? So it's all about like how we can reduce the one problem into the another one, right? So NP-hard problem, any problem you can say, like we have non-deterministic polynomial time algorithm for the satisfiability we have. That's why it's also come in the category of NP complete. What it mean actually? First possibility, first thing that you have to mark here, find the non-determinate, find the relation between the non-deterministic, जो भी whatever you have taken, find the relation or convert exponential problem into the polynomial time problem, right? Polynomial time problem. And next thing that we have to focus here, if you are doing this work, that means you are taking the problem as a NP-hard problem, right? But along with this one, if we are able to find the non-deterministic, if you are able to find the non-deterministic algorithm, then you can say this particular problem is NP complete. So if you are able to find this first point, you satisfying the first point but not able to find the non-deterministic algorithm, then you can say the problem is NP hard. If you are also able to find the non-deterministic algorithm in polynomial time, then it will become NP complete, right? So if satisfiability is there, I'm taking, and it is reducible to L, that means it's NP hard. If this L problem is able to find the non-deterministic polynomial time algorithm, then it will become NP complete, right? It's up to this L problem. Is it having only the reduction with the satisfiability problem or also having the non-deterministic algorithm, right? So I'm just drawing here a diagram here. If this one is a P class and this one is NP and this is NP hard, then we can say satisfiability, this is NP complete problem because it is also, satisfiability is also having the non-deterministic algorithm to solve it, right? So solve the problem in polynomial time. So that's why if it is solvable in polynomial time, so and we have the solution for it, it's a non-deterministic algorithm also we are having for this, then this particular problem will come under the category of NP complete problem, right? So up to now we know like P is a subset of NP. I've already told you. Cook's theorem, what it said actually, Cook's shown here, like if this satisfiability problem comes under the NPC, what it means, if any NP problem which is hard to solve, that comes here in NPC. Like if any NP problem comes here in the category of NP, that means this P problem, this particular P circle will come here. And if it will come completely here in the NPC, then our task is complete. That means all the non-deterministic, which are hard to solve problem, if they comes in the NPC, then P will becomes equals to NP. That is possible to solve. So our main target is relate all the hard problems with the satisfiability problem because it is solved already before some time, before 10 years, like I don't know when it is calculated, like it is evaluated like this, that satisfiability problems comes under the category of NPC. After that, like our research problem comes into the track when we get that satisfiability problems comes into the category of the NP complete problem. And if we know this thing, now our main purpose is to relate remaining algorithm with this algorithm only, right? And if it is possible to find all the hard problems, if it is possible to relate all the hard problems with this satisfiability problem, then we can say NP is equals to NP. That is the Cook's theorem actually, to relate it, right? So that we will discuss later. So up to now, I hope it is clear to all of you. So NP completeness, it is showing here the Cook's theorem actually. So what it is actually, a decision problem L is NP hard if L dash can be reduced. This is also from like polynomial time reduction symbol here. Either you can use this one or this one, right? In the L, for all L belongs to NP, then we can give the NP complete problem. Like L is must belongs to the NP, and it also belongs reduced in polynomial time. So for both the things it is clear, like it is NP hard and this is NP complete one, right? Reduction only, then NP hard. With the reduction you are having the non-deterministic polynomial time algorithm, then it is NP complete, right? So P class problem, NP, NP hard and NP problem. This is shown here as we have already discussed. So if any NP complete problem is solvable in polynomial time, that is the key point of the Cook's theorem that I have mentioned to you. If any NP class problem is solvable in polynomial time, then we can say every NP complete problem is solvable in polynomial time, right? Conversely, we can prove any complete problem, NPC problem, cannot be solved in polynomial time, then every NPC problem cannot be solved. Like one cannot be solved, then all will not be solved. If one can be solved, then everyone can be solved. Up to now, we know SAT, satisfiability problem, is a NPC problem and it can be solved. That means all other NP problem can also be solved. NPC problem can also be solved. So our main task to comes here all the NP problem under the category of the NPC, and to bound the P class to the NPC in order to satisfy the Cook's theorem, and it will give you the statement here and P is equals to NP here. So you can take an example in order to show this problem, right? So next we have reduction. Of course you can reduce it. If you have an NPC problem, then you can reduce it. We know, we have already discussed this thing, no need to just spend time on it. So NP problem example, you can see satisfiability problem. I've already told you there are two key points here. Like if find the solution, I've already told you, that is in the polynomial time, or do the reduction and compare it, or find the relation in between the already solved problem and unsolved problem. If one problem is having the solution and comes in the category of NPC, other can also be solved. So one note points are here, then you can note it. Both the points here, these 2 points, if one point is clear, first point is there, then comes into the category of NP complete class. If you satisfy only second point, then it will comes here in the category of NP hard. Reduction only, NP hard. If with the reduction you are having the algorithm, non-deterministic polynomial time algorithm, it will come NP complete class category. It will come in the NPC class category. So I have already given you the summary also for all the things whatever we have discussed in this lecture. According to the decision problem, if you say it is comes in the category of NPC, we have a diagram here. For that diagram we will discuss in the upcoming lecture. These are some problems. Like we know NP problem, but NP problem circuit satisfiability, that we have already discussed. Satisfiability problem, under which we have discussed the 3 CNF. That comes under the category of what? NPC category, right? Now this problem we have already find it out in this lecture. In next lecture we will discuss the clique problem, that can also be like clique problem, vertex cover and this subset cover. These problem we will discuss in the next lecture. So stay tuned with the lecture. Thank you. Have a nice day.